Hello, my name is Dr. Roderick L. Roll, and today I will be talking to you about the properties of water. We just finished talking about intramolecular forces. These are forces that are created between elements. To create these forces, we will create either a covalent bond or a ionic bond. We also talked about intermolecular forces. These are forces between molecules themselves. The examples were the hydrogen bonds. This will create a dipole-dipole moment. Water has a dipole-dipole moment. So does acetone and methane. This slide shows the actual dipole-dipole moments of many molecules: ammonia, ethanol, methanol, and so on. So the intermolecular forces that creates these hydrogen bonds, they hold ethanol to ethanol and water to water. We're going to demonstrate which one has the greater dipole-dipole moment. So the dipole-dipole moment can also be called hydrogen bonds, or it can also be called cohesive forces. Cohesive forces at the surface of liquids are the strongest. They are so strong that some insects are able to utilize this strong cohesive property. They can walk on water. So now we're going to look at several properties of just water itself. The first property is the stickiness. Water can be separated into cohesion and adhesion. This deals with the stickiness of water. So the first one we'll look at is cohesion. Cohesion is when water molecules stick to each other. That creates surface tension. This will help water to creep up the xylem that is found in plants. So water for a plant is gathered from the roots, from the ground. But how does it get up to the top of the tree? In the trunk of the tree, you have these sieve tubes. They're like small molecular straws that are made of wood. In those small straws, water will travel up the straw. How? Through adhesion and cohesion. Water that is below will be attracted to the water that is above. This is cohesion. This is how it moves up the tree. Again, that cohesive property is also strong enough that a water spider can walk on water. The second portion of the stickiness of water is adhesion. So water has the ability to stick to other molecules, such as the molecular straw, the sieve tube. All right, so water creeps up this sieve tube in the trunk called xylem because of adhesive properties and cohesive properties, the stickiness of water. In this slide, we're showing you what the meniscus is. When water creeps up the side of a graduated cylinder or a test tube, that is referred to as creating a meniscus. But what we're interested in is, why does it creep up? Because water is attracted to other things. It has adhesive properties. In this image, taking what you know now about adhesion and creating the meniscus, what is the proper measurement? Is this 66 milliliters or 72 milliliters? The answer was 66. So this is an experiment that we will perform in class. Compare surface tension of different mixtures by adding drops on a penny. We will compare ethanol to water. So water that sticks to the penny is sticking to something else, that is adhesive properties. And the water sticking to itself is cohesive properties. So we're going to look at these two mixtures to see which one has better cohesive properties. You will add drops of water onto a penny, and you will add drops of drops of ethanol to a penny, and you will tell me which one holds the most water. Therefore, it would have the greatest amount of cohesive properties and adhesive properties. The second property of water that we will talk about is the moderation of temperature by heat. Water has a high heat capacity. This means it is able to absorb a lot of energy before it changes in temperature. To illustrate this, you could put water in a pot and ethanol in a pot. Put both of them on the stove and turn them on. The ethanol would boil immediately within 2 minutes, whereas water would take maybe 5 to 10 minutes to boil. This means water absorbs a lot of heat energy before it changes in temperature. So it has a high heat capacity. This can be seen when we look at coastal cities versus cities that are inland. If we look at Cedar Key versus Gainesville, the water that is on the coast absorbs a lot of heat. Therefore, the coastal cities should be cooler than the inland cities. The opposite will happen in the wintertime. The warmer waters will release energy, therefore making the coastal cities a little warmer than the inland cities. Specific heat of a substance is defined by the amount of energy required to raise 1 gram of that substance by 1 degree Celsius. So in this image we have several different compounds, several different molecules. What we're looking at is to see how much energy can they take before they change in temperature. So they measured out 1 gram of water, methanol, steam, benzene, wood, soil, and so on. And they added heat to it. And then they measured the temperature change. And as you can see, water absorbed the most heat before it changed in temperature. It absorbed 4,186 joules of energy. So it has a very high heat capacity. This slide shows other representatives in that same experiment. Copper, 385 joules of energy. Iron, 450. And water, 4,181. So that much energy is needed to raise 1 gram by 1 degree Celsius. The heat used to create the 1 degree Celsius change is denoted in terms called calories. So in physics, you'll use the terms joules, but for natural science purposes like biology and anatomy, we'll use the terms calories. So be able to convert 1 calorie is equivalent to 4.184 joule. This slide talks about a interesting fact about calories. 1 pound of muscle versus 1 pound of fat. 1 pound of muscle gained over the summer is going to raise your resting metabolism by 35 to 40 calories per day. Versus if you gain 1 pound of fat over the summer, it is going to raise your resting metabolism by 2 calories per day. Some more interesting facts about fat versus muscle. Fat would actually take up more space in your body than a muscle, so you would appear to be larger. So these are some other properties of water that you probably already know. Water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. And at room temperature is typically between 20 and 25 degrees Celsius. 2b, high heat of vaporization. So water can absorb a lot of energy before it turns into a vapor, before it evaporates, before it turns from a liquid to a gas. 1 gram of water at room temperature takes 580 calories of heat to go from a liquid state to a gaseous state. The bond that will be broken in this experiment would be the hydrogen bond. The third property of water is expansion upon freezing. Normally, hydrogen bonds are constantly breaking and reforming. But as you chill the glass, this breaking and reforming is going to slow down. As it approaches freezing, which is 0 degrees Celsius, the breaking and reforming is eventually going to stop. Then you will form this very structured crystal lattice. In this lattice, you have created a hexagonal shape of water. The fourth property of water is its versatility as a solvent. We talked about water being the universal solvent. Why? Because it has polar properties. It has slightly negative and slightly positive charges. So water dissolves ionic substances. How? It will form a hydration shell around them. So in this image, you see that sodium, which is a positive cation, is totally surrounded by water. The portion of the water that is attracted to the positive sodium is the slightly negative oxygen. The other element in salt is chlorine. Chlorine is an anion. It is negatively charged. So the slightly positive charges on the hydrogen of water will be attracted to that. This image shows the salt crystal being totally dissolved. The fifth property of water is its reactivity. Water is very reactive because it is an important part of metabolism. In the top image to the right, we're looking at a sugar. Let's say it is a polysaccharide. Water is needed for the enzyme to break the polysaccharide into the individual glucose monomers. So water is needed. So water is reactive in the metabolism in humans and animals. The bottom image shows dehydration. When I'm going to take glucose molecules and form glycogen, a polysaccharide, water is going to be released from this chemical reaction. This is a concept map taking all of those properties of water and linking them together. So water has two sides. It has a slightly negative side and a slightly positive side. The slightly negative side will be the oxygen, and the slightly positive side would be the hydrogen. So water is going to create a dipole. Now you will utilize this water molecule kit to perform a few demonstrations in class. Using the water model, demonstrate an ice lattice. This should be a hexagonal shape when you take several of those water model kits and put them together. Even kids can do it, so it's easy. This is how a snowflake would appear. Create several of those hexagonal structures with the models and then piece them together, and this is how a snowflake would look or appear. Using the water model, demonstrate the liquid form of water as it would appear in xylem of a plant. Even kids can do it. You just line them up in a single file line. The bottom water molecule is attracted to the water molecule that is directly above it. So in plants, capillary action is how it gets up the stem, and it's nothing but cohesion and adhesion working together to get the water up the xylem of the plant. This is what surface tension looks like. You could place the water together, link them together, and put your pen on top. That would be surface tension. Using the water model, demonstrate the gaseous state. Remembering that when water boils, you break the hydrogen bonds. So therefore, none of your water molecules should be linked together. Using the water model, demonstrate how a salt crystal in water would appear using the model. Remember that the salt crystal is not fully separated. Salt is sodium chloride linked together by an ionic bond or ionic interaction. Using the water model, demonstrate how a totally dissolved salt crystal in water would appear. So now, totally dissolved means you separate the sodium and you separate the chlorine. Show how ethanol bonds to water. We will skip this, but this is how it will look. Using the water model, demonstrate how a nonpolar ethanol is not miscible with polar water. We will also skip that.